thanks for joining us. This is our first Oregon Beaches Forever webinar of 2026. So I'm very excited to welcome Paul Morgan tonight. But first, I'm going to tell you a little bit about Surfrider and the Oregon Beaches Forever campaign. So my name is Kaya Hazard. I'm Surfrider's Oregon Regional Manager. Surfrider is a nonprofit organization, and our chapters in Oregon work to protect our ocean, waves, and beaches through grassroots organizing and advocacy. So we work on issues like plastic pollution, water quality, beach access, and coastal resilience. So to that end, Surfrider has teamed up with Oregon Shores to work on our Oregon Beaches Forever campaign. Through this campaign, we're taking a holistic approach to protecting our beaches. So we're not only opposing harmful shoreline armoring along our coast on individual and beach-wide scales, as is the case with Beverly Beach, but we're also working on nature-based solutions to erosion control, which will help to promote beach preservation and climate adaptation so that we can move away from hardened shorelines. We're also advocating for local level climate adaptation and improved shoreline management at the city and county level. And recently, we've been working with state agencies on their rulemaking processes to update and improve existing regulations for shoreline armoring, permitting, and access to and along the shoreline. So if you would like to learn more about this campaign and stay up to date with upcoming educational events like this one, you can find more information on both Surfrider and Oregon Shores websites, and I'll drop those links into the chat shortly. And with that, I will turn it over to Mandy with Oregon Shores.
Thanks, Kaya. Hi, everyone. Thanks for joining us tonight. My name is Mandy Watson. I'm the Coastal Policy Manager for Oregon Shores. Oregon Shores is a nonprofit that focuses on ocean and coastal issues all up and down the coast here in the state of Oregon. And our vision is a healthy and resilient Oregon coast where people and nature thrive together. And we work towards achieving this by educating and empowering people to protect their coastal ecosystems as well as coastal communities. And we do this work through kind of two main avenues. We have our policy advocacy team and our education and outreach team. We have a wonderful youth education program, and we're widely known for our Coast Watch program, where people adopt a mile of the coast to monitor and steward and contribute to a statewide citizen science project. As Kaya was mentioning, we have a strong policy advocacy team, which spans from influencing land use and shoreline planning decisions with Kaya and our Oregon Beaches Forever team, to lobbying for coastal habitat protections at the state legislature. And I also wanted to open with some great news tonight that the 2.5% for wildlife bill just passed the Senate. So that's some great news for Oregon wildlife. And we're also super lucky. Some more great news is we have Paul Morgan with us tonight. Paul is currently a PhD candidate in the Department of Earth and Space Sciences at the University of Washington. His research at UW focuses on the impact of landslides, both in generating hazards and in altering the shape of landscapes. Before coming to UW, Paul completed a master's degree at Cornell University, where he studied uniquely preserved rockfall deposits in the Atacama Desert. He also worked at the Earth Observatory of Singapore, where he studied earthquakes off the shore of Sumatra, Indonesia. He began his scientific career at UC Santa Cruz, where he majored in earth science and studied seismic signatures of ocean waves crashing on sea cliffs, which sounds super cool, Paul. I wish we could have you for 3 hours instead of the hour that we have you for. But with that, I will let you take it away and get into it. Thanks so much for joining us.
Let's get my slideshow going. Okay, does this look good?
That looks great.
All right. Well, thank you for that introduction. Thank you for having me at this Oregon Beaches Forever seminar. I'm sorry to say I will not be going to the beach today, but I'm still excited to talk to you about the Oregon Coast Range. And I'm going to talk to you about landslide dams, a hazard that you may not have heard of before. But before I do that, I'll introduce myself. My name's Paul Morgan. I'm a PhD student at the University of Washington. And when people ask me what I do, I say I study landslides, earthquakes, mountains, and rivers. I would call myself a geomorphologist. And geomorphologist, geo meaning earth, morph meaning shape, is someone who studies the shape of the earth and the processes that shape it. Sometimes we go out along rivers and measure rocks. Here's my lab mate measuring a rock. Sometimes we make what I think are really cool simulations of landscapes. This one I made includes landslides, no surprise there, to learn how landscapes are formed. But the processes that form landscapes are often also natural hazards. And so we also study natural hazards and how they impact people. These are two pictures taken from storms just this winter, one in Oregon and one in Washington, showing flooding and landslides that can affect people. So coming back to our title slide, I'm going to talk about landslide dams. I'm going to tell you what they are and where they might happen next. To give you a little guide on what the talk will look like, I'll spend the first part of the talk going over what the deal is with landslide dams. This will mostly be a story time where I'll tell you about these crazy events that have happened in the past. And I think by the end, you'll be convinced that we should care about them. Then I'll talk a little bit about the methodology we use to figure out where they might happen. And I'll spend some time there talking about the Oregon Coast Range, why we use that as our study area. And then at the end, I'll let you know what our results are, and I'll end with a couple takeaway messages. So what's the deal with landslide dams? Well, the picture that you've been looking at behind the slides is a picture of a landslide dam. This occurred in Chilcotin, British Columbia, a little bit north of Seattle here. What we're looking at here, we see the normal hill slope behind, and then right around here is the head scarp of a landslide, and this whole mass of land, soil, trees, and all fell down into this river valley. It has blocked the river, so now there's a lake building up behind the landslide, and you can see that the river valley down below the landslide is totally dry at the time that this picture was taken. So a landslide dams the river. At the start, that causes water to build up behind that landslide, creating a lake upstream. In this case, the lake went for tens of kilometers upstream. You can see how it floods anything that's there, whether it's houses, trees, or a road. But actually, the real danger comes in what's happening now, which is that this dam was not built to code like a human-built dam, but rather it's just a pile of dirt. So once the lake starts to overtop the dam and breach it, you get a dam breach and what we call an outburst flood. Here you can see that again, a little slowed down. Look at these trees. So once the water starts flowing over the dam, it starts to erode the dam away, which allows more water to flow with more power and cause more erosion, which leads to this runaway effect and a cascading landslide dam. Catastrophic outburst flood is what we often call them. Here's a picture of a video taken right when the water started to overtop the dam. You can see it sort of eating its way through the top of the deposit. This was taken just a couple hours later, and you can see all of that water rushing over the dam, flowing with all of the debris in it. And then a few kilometers downstream, 12 miles downstream, you can see it's still that powerful flood wave is eroding the banks, causing havoc. This outburst flood happened while I was already studying landslide dams. I was following it closely. And between the time of the dam and the time of the flood was about 5 days. And it's not hard to imagine how an event like this could be fatal. Here's a list of a few landslide dam events, their locations, their dates, and the fatalities from these events. And I'm sorry to say there's a few events that have caused quite a few deaths. And I'm sorry to say that just this last year, I had to add a new row into this column, which is this landslide dam disaster that happened in Taiwan. Here, we can see a picture of what's going on. There's a big landslide, a really absolutely massive landslide that was triggered first by an earthquake and then by a typhoon, caused a really large lake to back up in the mountains. And then another typhoon caused that lake to build up over top and flood downstream and flood into the city of Guangfu. Here you can see the power of that flood. Now, these aren't normal floods. They're extra powerful, extra strong floods. They flow down with the strength maybe more like a tsunami, and they're full of debris. So not only do they bring a lot of power, enough power to like destroy the bridges, I think this video is wild, but they bring so much dirt from the landslide that they fill up the river and can change the path of the river as it goes. So they can change the path of the river flooding into a city, like happened to the town of Guangfu. Now, there was an evacuation order issued for this town, and tens of thousands of people did evacuate successfully, but the evacuation order didn't reach everyone. And the flood waters rose so fast and were so full of sediment that some people couldn't get out of the way in time. There has been a fatal landslide dam disaster in the US. In 1925, the Gravant slide in Wyoming, another large landslide, created a lake. The local surveyors said, we think this will be stable, we're not worried about it. But then the next wet season, a landowner saw a hay bale that used to be floating in the lake fly by him on the river. And he got in his Model T and raced down into town within 15 minutes, got almost everyone in the town to evacuate, except for a few people who refused to evacuate. And now the town of Kelly, Wyoming was destroyed, was wiped off the map. But it's not all hopeless. Just less than 50 years later and 60 miles away, another landslide dam occurred, this time after the Hebgen Lake earthquake, or sometimes called the Yellowstone earthquake, triggered this landslide that blocked the Madison River in Montana, building this lake behind the landslide. But this time, the Army Corps of Engineers bolted into action and excavated a spillway in less than a month. And the reason we excavate spillways is so that, one, the water has less height to grow. The lake will be smaller when it overtops the dam. And second, to sort of stabilize the flow once the water does overtop, to prevent that runaway breach outburst flood effect. And it worked. They stabilized the flow, and the lake is still there today. Actually, I drove past it a couple years ago. It's beautiful. There's a really cool visitor center on top of the landslide deposit. And these are some trees that were flooded by that landslide. I'm doing great on time. We're going to keep going with story time. Another example of a really incredible remediation effort is the Tangshan landslide. This landslide was triggered by the 2008 Wenchuan earthquake in Sichuan, China. This was in the mountains upstream of a really densely populated region. So actually over 200,000 people were evacuated. And this was right after the earthquake. And also they airlifted excavators onto the inaccessible landslide dam. Fortunately, there were no fatalities from the flood. They were able to excavate a spillway. They knew when the flood happened. There was a flood into the town, but everyone was evacuated. I think I have one more story before getting to the rest of the study, and that's the case of the Thistle, Utah 1983 landslide dam. This flooded the town of Thistle, which is now a ghost town. Nobody lives there anymore. But what I think is really exciting about this one is how the railroad company, the state of Utah, and Army Corps of Engineers worked together to stop this from ever overtopping. They installed these pumps to lower the water level of the lake, and actually the railroad dug a railroad tunnel around the landslide dam. So now this river flows through a railroad tunnel instead of over the landslide dam, which I think is just absolutely wild. Um, so bringing this back together, we see that between the time that the landslide dams the river and the time that that river possibly overtops and turns into a catastrophic flood, there is space for a response to avert disaster, but it has to be quick because most landslide dams fail and most fail in 10 days or less. So we think that this necessitates pre-planning, and the first step to that pre-planning is figuring out where it could happen next. So with all those stories, hopefully I've convinced you that landslide dams are worth thinking about. They are scary, but looking on the bright side, a quick response can prevent disaster. So next, how do we figure out where they might happen? For that, we want to start with a regional study. We want to look at a broad region, figure out first, what's the general susceptibility, how likely it is that these might happen in the region, and then identify hotspots where maybe there's more or less landslide dam potential, and also learn where the magnitude of the hazard is greatest. Where could the biggest floods be? And for this, we take our analysis, our study as we make this new method to the Oregon Coast Range. And I'll spend a little more time building this up, telling you why we use the Oregon Coast Range, since we're in an Oregon Beaches seminar. But first, I want to say that actually the Oregon Coast Range for geomorphologists is a celebrity mountain range. It's in this sort of sweet spot where it wasn't glaciated, but there's still mountains. And also in a lot of it, the rocks are sort of similar. So it's really interesting for geomorphologists to study. It makes a great natural laboratory. But that's not necessarily why we're looking at it. We're looking at it because there are compounding hazards that could lead to landslide dams forming here, and there's a lot of good data in this area. The compounding hazards include subduction zone earthquakes. Here I'm pointing to our study area on the Oregon Coast Range. And so we expect a subduction zone earthquake to really shake this region. And when you get big earthquake shaking, you can get a lot of landslides. Earthquakes can trigger a ton of landslides. Here's another table with earthquakes, their magnitudes, and the total landslides they triggered. You can see many of these earthquakes have triggered tens of thousands of landslides, all in just a few minutes. And so it's no surprise that earthquakes can trigger landslide dams. For example, the Kaikoura 2016 earthquake in New Zealand created over 200 landslide dams. And the Wenchuan 2008 earthquake in China, which I mentioned one of the landslide dams before, triggered over 250 landslide dams. And even the 2001 Nisqually earthquake, a smaller earthquake we're actually approaching the 20-year anniversary of up here in the Puget Sound area, caused a landslide that dammed a small river in the Puget Sound. So we know there can be earthquakes that could possibly trigger landslides in this region. There's actually been quite a bit of study trying to look into what landslides from past Cascadia subduction zone earthquakes might look like. I'll touch on that a little bit, but not so much. But of course, also we have atmospheric rivers. It's a very wet region. This is a satellite image taken this last December of the atmospheric rivers coming. So I'll go on a little aside here and talk about why heavy rain leads to landslides. There's a few ways and a few types of landslides it could lead to. The first way is just by flowing over the surface of the ground. Normally when rain lands, a lot of it goes underground and actually enters the river through these underground pathways. But if too much rain falls too fast, the ground can't handle it all. And a lot of it will run over the surface, and then it'll pick up dirt, debris, branches, and that can lead to mudslides, or we call them debris flows, following ravines. These photos were taken on my local mountain highway, Highway 2, in going up into the Cascades from Seattle. just this last December. So these we call them debris flows. Another reason water can lead to landslides is because water is heavy. Like I said, it fills up all the pore space, all the little holes in the rocks, and that's just more mass that the ground has to hold up to keep from falling down. And then the last and possibly the most important reason is that heavy rain can go underground, either shallow or really deep, and it can find the cracks that maybe a landslide might fail on and make those cracks a lot slipperier, lubricate them so that it's easier for that land to slide downhill. This is a picture of the Siletz, Oregon landslide that hit the Siletz River also this last December. And this happened during a atmospheric river event, and that was probably the cause. So we have our compounding hazards, but also we have a lot of data in the Oregon Coast Range. We have a region-wide LIDAR DEM. So those are two acronyms. I'll go over them. Digital elevation model is what DEM stands for. That's like a picture of the landscape, and in each pixel you have the elevation of that pixel. So here is a map of a DEM of our study area, the Oregon Coast Range. The pixels are colored by their elevation. And then also we simulate a sun making shadows on the landscape to show the local relief, the crinkles of the earth. Geomorphologists love DEMs. Put me and my lab mates in a room with a DEM and we'll talk about it for days, loud and at length. Is how we'll talk about it. And then when it comes to DEMs made with LIDAR are king. That's because LIDAR, light detection and ranging, like radar, but with lasers, can see through the trees and can give you a picture of what the landscape underneath looks like. And thus, LIDAR DEMs have really revolutionized landslide science. Because before they existed, we would look at an aerial image or even walk in the forest and just see something like this, see trees. You can't really see much. Even with a low resolution DEM, it can be hard to tell what's going on. But when we use LIDAR to remove all those trees, the texture of the landscape can really come out to us, and we can see all these little bumps and hummocks is the word we use for them that show where a landslide happened in the past. And then an expert geologist or geomorphologist will go out there and map the extent of these landslides on LIDAR data sets. And that's the other data set we have. Geologists at DOGAMI, the Oregon Department of Geology and Mineral Industries, good thing that acronym was written on the slide, have created the Slido statewide landslide information database for Oregon. This is a open data set with in our study area alone, 18,000 mapped landslides. I've put them on this plot of our study area. They're these little red polygons. Here's a zoom in. It's a little pixely, but you can see in a lot of our area, mapped landslide deposits really cover much of the landscape. So this is clearly a region where there are lots of landslides. And then the last data set we're working with is this data set developed by one of my co-authors, Will Struble, and his co-authors at DOGAMI and at University of Oregon. And that's a data set of mapped landslide dam locations. So each of these yellow dots represents an usually ancient, but not always, some fairly recent, landslide dam that they mapped in the area. And actually, they visited about 20 of these and found forests that were flooded by the landslide dam, by the lakes growing, and used tree ring dendrochronology to date exactly what year these forests were flooded. They expected to find that all of these landslide dams might have happened during the 1700, the last great Cascadia earthquake, but actually they found all of them correlated with more recent atmospheric river events. So we know both of those are still things to worry about. But thanks to them and this study, we have this great data set of over 200 mapped landslide dams in our study area. And then the last reason we're looking at the Oregon Coast Range is because of our funders. This is funded by the Cascadia COPES Hub and NSF Research Hub. It's the reason why we're in touch with the Surfrider Foundation, and they make a lot of connections to local stakeholder organizations. And so I'm excited to be here and talk about this related to that. Okay, so hopefully I've convinced you that the Oregon Coast Range is a great place to study landslide dams and to make a new method for figuring out where they might occur. So what's our method? Well, to figure out where landslide dams might occur, I'm going to spend a lot of time on this plot. We'll call it the valley width volume plot or width volume plot. On the x-axis, we have the width of a valley, and on the y-axis, we'll plot the volume of a landslide entering that valley. So it's easy to imagine or picture if you have a really narrow valley and a really big landslide, you'll expect that to landslide to dam that valley. Whereas if you have a really wide valley and a really small landslide, you might not expect that to dam the valley. So let's populate this graph with data from the Oregon Coast Range. So we can add in all those mapped landslide dams by Will Struble and a few that we mapped ourselves on LiDAR. And we see the red dots are all landslides that did dam the river. And then we'll look at another set of landslides, and we randomly pick them from the databases, and we map in blue all the landslides that don't dam the river. And when we plot them all together, we see that they are in fact two distinct domains. When I first made this plot, I was really worried they weren't going to be separate and we would have to start over, but they work. It works. We can put a line there and separate our landslide, our dam forming domain and our dam not forming domain. But my co-author said we should be a little smarter than just putting a line right there. We can actually fit this with a statistical function. We can use logistic regression to fit a function where if we imagine all our landslide dams have a value of 1 and our non-dams have a value of 0, we can fit a function between those, connecting the ones and zeros. And actually, if we plot that over this whole area, it looks more like a surface going from 0 to 1. And here on a graph here, now we have a grayscale surface. The non-forming domain to 1 dark gray, the forming domain. And we call this metric, this 0 to 1 value, damability. So a damability value of 0 means you're likely not going to form a dam, and a damability value of 1 means you are likely to form a dam. So now, going back to a real landscape, we just need to measure the valley width across the landscape and estimate the landslide volume for future landslides on that landscape. To estimate the landslide volumes, we go back to that Slido database and we find that a log normal statistical distribution fits the volumes of the 18,000 mapped landslide deposits in our study area. I tried a lot of other things to be a little more clever, but none of them worked. So we'll use this log normal distribution and assume that future landslides map this distribution. And then to measure the valley width, I made a new algorithm that does math on those digital elevation models and measures the elevation of a cell relative to the nearest river cell. And it declares that if you're below a certain threshold, that cell is in the valley. And then we measured the width of those valleys along the river. Fun fact, these last 2 slides were like 2 full years of work, but now they're just 2 slides. But they are underpinning the results. So how do we estimate where landslide dams might happen? We use the damability function. Now we're on to the last bit. Where are they likely to hit and where would they be the most dangerous? So what are our results? Okay, let's go back to the Oregon Coast Range. These are the rivers we're working with. Here I've added and we can see some things to look at. where you might be looking at. And then through the rest of this talk, I'll put this sideways, and I'm actually gonna separate out the drainage basins. So I'll keep all the area that flows down and into one river in separate basins. So that's what these black lines are that you'll see. And I'm going to highlight two specific basins for a couple slides because these show how different our results can be. So these are our results. I'll take some time to walk through this figure. The colors go from 0 to 1. The darker values are higher damability, so more likely for a dam to form, and the lighter values are less high damability. In these two insets over here, we have the DEM gray scale on the back, and then our rivers are plotted as dots with the damability color that they are associated with. And then in this larger figure of the whole study area, the region is broken up into little hexagons, and each hexagon is colored by the average value of all of the river dots within that hexagon. So zooming in on the Wilson River catchment, let's look at our results. The first thing we want to know is, does it work? And to do that, we look at the places where the landslide dams are mapped and see if we had high damability values there. This plot shows the landslide dam susceptibility or damability values on the x-axis, and the y-axis is the number of points. And we can see that when we look at all the river points, most of them are small values, but when we look at just the landslide dam points, we see a lot of big values. This shows us that we're finding the landslide dams. And we actually identify this threshold, a damability value of 0.35 is the optimum place to say this river could likely be dammed by a future average landslide, so to speak. We call these dammable river points. But where are the rivers the most dammable? And for that, we'll look at this area. And now I have a new plot here. We have drainage area on the x-axis. So this is how much area is flowing through a river. So really big rivers are on the right and really small rivers are on the left. And we see almost all the high dammability values are in this small river area. And if we look at the map, we can sort of see the darker colors are often on these smaller tributaries and not the main stem of the river, and certainly not where the river is really big and flowing into bays. This matches these two other plots that both show as you get steeper slopes and greater average relief, you get increased dammability. So when we look at our plot of dammability on across the region compared with the elevation map, we see the more mountainous regions, there are more small mountain rivers, and these small mountain rivers have the highest dam potential. And I'm gonna color this in on this map over here and try to put all our results on one map. By each drainage basin, I'm gonna color in based on what percent of the points in that drainage basin are past that dam potential threshold, are dammable. So if you're the Wilson River catchment, I think around 80% of the river points in that catchment are dammable. So that's a dark gray over here. And then the Alsea River, much less are dammable. So that's a lighter gray here. And we see actually the lightest gray rivers are the ones draining inland towards the Willamette Valley. So those are the places where landslide dams are most likely to occur. But I'll show this, let this image play to motivate why actually we don't just care where they'll occur, we care about where they might make the biggest floods. Really incredible video. Fortunately, no one was hurt in this. This is the Chilcotin landslide dam event, and no one was hurt. People were evacuated downstream. So we care about the size of the flood, and the size of the flood is correlated to the size of the lake And we can use this relationship that other authors have found to predict the size of the lake. So basically, how big your lake is a function of how big your landslide is and how much drainage area is flowing through the river. So basically, how big your river is and how big your landslide is. We did this math on our data set, and we found that for those most dammable sites, if an average slide hit the river, uh, we would get lake volumes from as small as 10 meters cubed for the really small lakes up to 10,000 meters cubed. What does that mean? 10,000 meters cubed. That sounds big, but actually it's not that big. So I went back and found this USGS database of past landslide dams. I combed through it and found every event they described where the lake volume was estimated and the comments referred to what type of damage the landslide caused, the flood caused. There are about 50 of the pages out of 490 that both of these data were recorded. Here we have an event. This is one of the most intense landslide dam events, the 1933 Baiji River or Daishi Sichuan landslide dam event. Here, the river volume was 400 million cubic meters, or the lake volume. And in the comments, we can see the impact of this. The failure of dam caused a 60-meter high flood 3 kilometers downstream. And this event killed at least 2,423 people. And by looking at all these, we found that there is sort of a consistent threshold for catastrophic flooding, and that was a lake that was 1 million cubic meters, so 10 to the 6. If your lake is bigger than 10 to the 6, you're in the stage where you could see catastrophic flooding. So we're in the clear, right? I did the math just this last slide, and we were only at 10 to the 4. Well, not exactly, because remember I said it takes the drainage area and the landslide volume. Before I just used the average landslide volume, but we know landslide dams are often, or landslides are often dominated by the biggest landslides. So the landslide hazards are dominated by the biggest landslides. So we did those calculations again, but this time imagined that we had our 95th percentile landslide. So a landslide that was really big impact the rivers. And now we have a map of where that 95th percentile could both dam the river and that dam could make a lake that's big enough to cause a catastrophic flood. And it's a little hard to see in this, but these maps, that data set is plotted in yellow on this plot. So it's in yellow, we have places where a really big landslide could dam the river and that dam could make a big lake. And one thing you'll notice is that those catchments that are in the darkest gray here do not usually correspond with the places with the largest yellow rivers. And in fact, all of I call them the worst case rivers, are along the main stems and often fairly far downstream. And so the last thing I do to illustrate the hazard is to plot the places where we have both, where we're in a dammable river section. That's the average landslide could dam it there. The river is pretty narrow. The valley is pretty narrow. And where the river's big enough that if a big landslide happened there, it could create this dangerously large lake. And those points are plotted in red. So you can see there's only a few spots in red on this plot. And I think the next steps going along this axis, that this leads to is to look more in depth along these river corridors where big rivers flow through narrow canyons. So in the end, actually, our results reveal sort of a complicated hazard landscape. We found widespread high landslide dam susceptibility. There's a lot of gray catchments on this plot, and in fact, roughly 1/3 of the over 100,000 river sections that we did this calculation on were dammable by our measurement. But a vast majority of those dammable river sections would create relatively small lakes. However, large landslides could create dangerously large lakes. along a few of the river corridors in the region. So I think the next steps for this type of research would be to narrow in on these regions that are narrow and have big rivers, and to focus on the human aspect of this. In this talk so far, I haven't touched where people live, and I think that because this hazard landscape is a little complex, it makes sense to focus on actually where would a flood, outburst flood, actually impact people. I worked with a student intern to make some preliminary flood vulnerability and flood exposure maps. These sort of complicate the picture. Some of the more mountainous regions where they're more likely to be landslide dams have a lot less population exposure, but some areas like the Umpqua, where there are large rivers, still have a lot of people living along them. So to answer our question, where are landslide dams likely to hit, and where would they be the most dangerous? Well, it's a little complicated. Mountain rivers are places where landslide dams are likely. Big rivers are where landslide dams are scary, and big rivers flowing through mountains are probably the worst case, and that's where we should focus our attention on in the future. So I'm going to finish up by looking at a case study from the Siletz landslide that I mentioned earlier, that happened just this winter, and then some takeaway messages. So this December, right along the Siletz River and Highway 229, this landslide occurred. You can see the headscarp up here. A lot of the trees were just sort of rafted along. You can see their roots were in place. So this is a really deep landslide. The failure plane that the ground was sliding along was really deep. And it went into the river. A lot of debris was washed downstream. In fact, ODOT picked up some of the debris at bridges downstream, and it destroyed several houses. So when I thought, oh, I better think about this. Oh, and last thing, I did talk with someone at Dogami who said that the local emergency managers took this event really seriously, and I think they even collaborated with the Army Corps of Engineers to run some hazard models to see what the impacts of this could be. So there are other people in the world that know a lot more about this landslide than I do from Googling it earlier today. But the first thing I do when I want to know about it, you know me, I'm a geomorphologist. I love DEMs. So I'm going to look at the LiDAR DEM. This is from the Dogami LiDAR viewer. You can just, this is a screenshot from the website. You can look at that wherever you want. This is where the landslide occurred. Here's another picture of that landslide. I've mapped it out here. And when I look at this landscape, I see a lot of these sort of arching, almost look like ice cream scoops out of the hillside. We call these headscarps. And I would say there's been a lot of landslides here, probably ancient landslides in this region. So it's not especially surprising that we would see a new landslide in this area. I can also estimate the size of the landslide and measure the width of the valley and see where it falls on our damability plot. We get a value of a little over 0.1, so it's not 0. And certainly if it mobilized, it wouldn't be surprising if it dammed the valley. But there is this little, my valley width estimate was on top of this little fluvial terrace or bench here. So it's more likely that I could dam the smaller river, but maybe wouldn't cause as catastrophic a flood. And then thinking about our flooding map, where are we? At first I was afraid that maybe this landslide was in one of these areas, but actually it's here. This is not in one of our worst case lakes, but the river is really big here. And so if the landslide were to dam it completely, if there were an anomalously long run out by this landslide, it could lead to some serious flooding. So this has been a talk about hazards, and a lot of the stuff that I talked about are things that get responded to at the government level, the Department of Transportations, the Army Corps of Engineers, emergency managers making evacuation decisions. And there are a lot of people with this on their radar once they happen. But I think this study by a couple of people from University of Washington from the civil engineering department can shed some light on what the rest of us can do in the case of a landslide or to limit our landslide risk. In this study, they looked through data from all sorts of real landslide events and survivor accounts. They asked how did the people survive, what did the people who survived do, and what did the people who didn't survive do. So this is some lessons to learn. What can you do? Before an event, the first thing to do is be informed about the potential landslide hazards in your area. I pulled up here, I went to the Oregon statewide geohazards viewer. Dogami has these great portals that have maps you can look at. This is my favorite place along the Oregon coast, the town of Manzanita. And so I thought I'd look at some of the landslide hazard layers available on this geohazards viewer. You can put building footprints on there. And of course, the first thing I do is put on a DEM. I want to see what the landscape looks like. There are definitely some steep slopes up here, and maybe even some of those ice cream scoops in this northern part. They have some other layers. There's a statewide susceptibility estimate that Dogami has put out. I actually use this in my workflow to estimate landslide dam susceptibility. It's a fairly coarse resolution estimate, but it's something is better than nothing. We can see this area with the steeper slopes and those ice cream scoops is plotted with high landslide susceptibility. And depending on where you are in Oregon, there are other regional studies that show up. So you can see this study doesn't cover the entire map area, but it really highlights these, what I highlighted before. Someone had probably mapped these as past landslides, and past landslides make new landslides more likely to occur. So there's the highest landslide risk right there. So if you live, I would recommend looking at something like this around where you live to see if there are landslide hazards in your area. And if you're on a slope with landslide hazards, one thing you can do before the event is move your areas of high occupancy, like your bedrooms, up in the house and to the downhill side. And that's because landslides can bring sediment and dirt and mud into the house. So during a landslide event, what should you do? Actually, I listened to a short interview with the people who lived in one of the houses that was destroyed by that Siletz landslide event. And people who are around landslide events often describe it as they hear it first. It's often really loud, a rumble, like a train is running through the house. You often hear cracks of trees breaking. Those people were able to get out of their house and escape before the house was washed away. But if you're not, you should go upstairs, again to the downhill side, stand on a counter, anything to get up as high as you can. And then avoid places with lots of furniture. Don't hide behind a big cabinet. And then also, interestingly, open downhill doors and windows. Let the sediment that comes into the house escape. And then, God forbid, you're caught in a landslide. Continue to make noise and motion as soon as the landslide happens. Actually, most rescues are done by neighbors. And things you should not do is open a door out of curiosity and shelter behind large furniture. So bringing that to landslide dams, what can you do in the case of a landslide dam event? Well, first off, I think my research has shown that we should not be surprised if a landslide dams a river in the Pacific Northwest, especially if there's an earthquake or a few atmospheric rivers. There are lots of places where landslides can dam rivers. And the telltale sign that a landslide has dammed a river is that actually the river water level will drop. Maybe the river will go dry, like we can see in this picture, like happened at the Chilcotin River. If you're in a river, especially if it's really raining and that river goes dry, you should probably get out of that river or get out of near the river and contact emergency authorities. And then also look out for that, especially during large storms and after earthquakes. And if the authorities issue an evacuation warning, please heed it. Get out of there while you can. So with that, I'll put up this little flyer that I made to summarize our findings that I can send to anyone who wants. And I'm here for questions. Thank you for listening.
Thanks so much, Paul. That was awesome. You have great science communication skills. So I really appreciated you interpreting the data for us, breaking down the acronyms, and making it just like so applicable to anyone. So I really appreciate you for that.
Thank you.
Yeah, also definitely a new fear unlocked for me. I haven't considered landslides before, and I'm also surprised not more people don't talk about this, like kind of in relation to the Cascadia mega thrust tsunami event. Like this seems like it would also play such like a devastating role in like the compounding forces that make that event super scary.
Yeah, we do a lot of, that's one of the reasons why one of the main motivators why we came into this project is we were thinking about all of we call them the cascading hazards, the things that happen after an earthquake. And the things, if an earthquake triggers lots of landslides, one, those landslides can cut off, can destroy roads and isolate areas. That's pretty common for large earthquakes. Uh, and then also these landslide dams, they can make the landslide dams. And so that's why we were thinking about the future Cascadia earthquake when we came into the study, thinking about, okay, where could landslide dams happen near us? And then one other thing I'll say is I showed a lot of scary examples, but in general, they are fairly rare. So that's one reason why they're not on the tip of everyone's tongue.
We do have a question in the chat, and feel free to type your questions in the chat, or if you want to ask your question directly, you can raise your hand, I believe, and we can unmute you. So this question says, if there was a major earthquake, how many landslides could be triggered? And I assume this is in relation to a Cascadia event.
That's my mom. Thanks, Mom. That's a great question. Uh, the truth is, there are some relationships between how big an earthquake is and how many landslides it can trigger. But actually, these relationships fall apart when we think about subduction zone earthquakes, like the Cascadia subduction zone. They actually, because they are offshore, away from the steep topography, and often happens fairly deep, they trigger a lot less landslides uh, than we may expect compared to something like the San Andreas Fault. Uh, so actually, people in our research group have spent a lot of time looking for landslides triggered by the last subduction zone earthquake. There may be some evidence along sea cliffs that may be past landslide deposits we can see on sea cliffs are had to have been triggered by earthquake shaking because they're so big. But inland, there's not a ton of evidence for earth landslides from the past Cascadia earthquake. To give some general ballpark estimates, I think one thing we can compare it to is the Tohoku 2011 earthquake. And the Tohoku 2011 earthquake triggered around 2,000, 3,000 landslides, which is still a lot. And if they impact roads, it can be really bad. But in the scheme of earthquake triggering landslide events, that's not nearly as many as, say, 10,000, 20,000, 100,000. So often on the scale of thousands to tens of thousands. And actually, I gave a talk at a subduction zone science seminar, and I went through back of the envelope calculation with our data set to see, using that 2,400 number, how many landslide dams could be triggered by a subduction zone earthquake. I think our data set, and I made a lot of assumptions, and I think it's a pretty high estimate, so these plots are a little confusing, but the takeaway is that earthquake could trigger dozens of landslide dams. I would not be surprised. Now, they may not all be big. Some of them may, some of them might not. Yeah, and I promise I didn't plant that question.
We have another question here. Is there a difference in the number of landslides triggered by an earthquake if the earthquake happened during the dry season versus the rainy season?
That's my wife. I promise I didn't plant this question either. Yes, there's a big difference. If your earthquake happens during the rainy season, uh, you can cause a lot more landslides because the landscape is full of water, and a lot of those failure planes that the landslides could fail on already are lubricated with water. Uh, this is maybe the case for the 1989 Loma Prieta earthquake in the San Francisco area. That earthquake happened right at the very end of the dry season. So even though it still triggered, I think, 10,000, 11,000 landslides, that's quite a bit fewer than we would have expected, say, if that earthquake happened in February or March. So that was, in some ways, lucky timing for that event.
Um, and then we have a comment here in the chat. We will send out a link to that HADSVU viewer so that you guys can all play around with it. We'll send that out after the webinar, along with a recording in case you want to watch it again or share it with a friend. We'll be posting it on our YouTube.
Yeah, I guess we'll give it a couple more seconds, see if there's any last minute questions. But if not, Paul, thank you so much. This was so so much fun and I learned a lot. So thank you.
Thank you for having me.
Okay, I see Susan raised her hand, so I am going to unmute you so you can ask a question. Okay, Susan, you should be allowed to unmute yourself.
Okay, can you hear me?
Yes.
Actually, I did put a question in chat about the Nehalem River, and when were you responding to my question about where I can get the Nehalem River mapping? Because I saw it was very red.
Yes. Well, the maps that Paul has shared with those like yellow and red spots, well, Paul, I'll let you answer if you're willing to share those out.
Um, yeah, so I can send this flyer. This flyer should be on the COPES Hub website shortly, cascadiacopeshub.org. I don't think it's on there yet. I just checked, but it will be on there shortly. Uh, and I would say, yeah, in response to like thinking about your specific river in your backyard, I think you probably know that river better than I do. The Nehalem, you're right, there is a lot of red spots on that. It does flow through right here. There's a pretty mountainous region and a fairly narrow river set there. Now, that said, I think that we should treat this map as a pointer for future studies. So I think probably the county emergency managers and state geologists have thought more about landslide risk along that specific river corridor. Uh, so they'll have a better estimate on like how big a specific landslide could be on a specific hill slope, whereas this was sort of a more regional look. But I do think, yeah, it's something to consider. And
Can I?
then the other thing I have to say is when it comes to these floods, I think it's still not clear to me how far downstream from the flood the impacts will be really intense. It will really depends on the landslide deposit specifically itself, something we can't predict ahead of time, how stable that deposit is, whether it's made of sand or big blocks, and then how fast the river can erode through it. Sometimes the deposits are really strong and it takes the river a long time to erode through it. So we end up with not really a flood on the other side. And sometimes the deposits are really weak and there can be a large flood.
Can I ask you another thing? I commented about the Highway 26 bridge coming down at the Nehalem. And downriver from that, other than some friends of mine that I've said if the rivers dries up, get out of there. The next big population area actually is the town of Nehalem. But that's, I don't know, 20 miles, 25 miles downriver. Is it possible that Nehalem would be impacted by the 26 bridge collapse when it opened up again, when the Nehalem overtopped it and eroded it, etc.?
Hmm. Yeah, again, I'm not totally certain how far these impacts will go downstream, but and then also how the flood wave spreads out or doesn't spread out if you reach into an estuary area or something like that. So things like that will really change, and I think for that type of thing, uh, the the flood hazards from this type of flood are really analogous to flood hazards in general. And so I think looking at that hazard visualizer and the flood layers in it are the way to go. But yeah,
Hmm.
I think you have really good questions, and I would love to have better answers to those. I hope maybe someone will pay me to find the
There you
answers.
go. Thank you.
Yeah, thank you all so much for your great questions. 7:03, so I think we will call it for the night. Paul, thank you so much again, and thanks everyone for coming. As Kaya said, we'll send out the recording and then any relevant links that Paul lets us share with you all. So thank you and have a good night, everyone.
Thanks so much, Paul. Thanks,
Thank you
everybody.
all.